everyone. To not delay the talks anymore, we're going to start with Wyatt Bain. He received his undergraduate degree in geology and geophysics for the University of Wisconsin. During that time, he worked for the Wisconsin Geologic and Natural History Survey in their bedrock mapping and sampling program. Following a short period as a contract geologist at the Hecla Greens Creek mine on Admiralty Island in Alaska, he began a master's working with Dr. Gene Klein. His master's focused on the evaluation of an exploration model for porphyry copper moly prospect in northern Arizona using fluid inclusions. In September of 2020, Wyatt defended his doctoral dissertation at the University of Alberta, working with Dr. Matthew Steele McInnes. His dissertation focused on characterizing the nature and evolution of ore-forming fluids in porphyry copper-gold systems and iron oxide-apatite deposits, and the later of which he will describe in the following talk. So welcome, Wyatt, and the screen is all yours.
Hello, and thank you so much for having me. It's really quite an honor to follow up what has been such a wonderful year of talks that have focused on IOCG and IOA systems. Over the next 20 minutes, I'm going to tell you about some of the work that I've done looking at the source and evolution of ore-forming fluids in IOA systems in the American Southwest. So to start my talk off here, I'm going to take you to what has become kind of the focal point for a lot of the discussion about IOA systems in recent years. This is the Laco volcanic complex, and it's located in northern central Chile, in the central. And this volcanic complex ranges from porphyritic to massive andesite in composition, and is associated with a number of andesitic volcanic complexes in the area. However, there's something very unusual about the Laco. And that's that the volcanic features in the system, or many of the volcanic features in the system, have a composition that ranges up to 90% iron oxide. And these volcanic features include very unambiguous things like laminated deposits of ashfall, which I've shown here on the lower right-hand side from Tornos et al. 2017. Volcanic bombs, volcanic domes, and large flow-like structures that have vesiculated center lines and emanate out from a central volcanic edifice and attached to dike systems that extend underneath the volcanic complex itself. Now, I like to start here because this really exemplifies one of the main points of controversy, or one of the main mysteries about IOA deposits, and that is, how is it that you get such unambiguous volcanic textures in rocks that have a composition that's up to 98% iron oxide? What makes the question a little more complicated is that in iron oxide apatites the world over, as well as in El Laco, there is extensive sodium and calcium rich alteration, a number of textural and geochemical features that are suggestive of a central role for hydrothermal processes. And as a result of the recognition of both these hydrothermal and magmatic features in IOA systems, there is a diverse array of genetic models that have been applied to these systems that span a spectrum between magmatic and hydrothermal end members. The magmatic models generally involve the formation of an iron oxide ore body via the emplacement and crystallization of a iron phosphate magma that's typically formed via liquid immiscibility with a parental silicate melt. And I've just shown a cartoon from Ho et al. 2017 that depicts how that happens. You start off with a flux-enriched silicate magma, and silicate magma undergoes immiscibility, and the iron phosphate magma coalesces within the magma chamber. And these models are quite compelling because they explain well the occurrence of volcanic and magmatic features in these systems, but they're somewhat problematic for a couple of reasons. For one, experimental models and experimental studies of the formation of these magmas indicate that the temperatures needed to stabilize such magmas can range up to 1400 degrees C, and in most cases are in excess of what's inferred for the formation of iron oxide apatite systems. Another problem is how would you emplace a magma that has such a dramatic density contrast with its silicate parental magma and form the unambiguous volcanic textures that we associate with these systems. Hydrothermal models generally involve the formation of an iron oxide-apatite ore body via the circulation of hydrothermal fluids that are of metamorphic, magmatic, or basinal origin. And I've just shown a couple of cartoons on the left-hand side of this slide that depict how that happens. On the far left-hand side, there's a scenario that's similar to porphyry deposit formation, where you have iron-rich fluids that are exsolving out of a parental silicate magma and are circulating up into the host rocks and forming the ore bodies via fluid rock reactions. And then in the center, I have a basinal model that's similar to like salt and sea type mineralization, where you have surface derived or basinally derived fluids that are circulated via magmatic and tectonic heat. In recent years, there have been a number of hybrid models also proposed for these systems. And on the right-hand side, I've just shown a cartoon of that from Adam Simon's group. In these models, the magnetite itself is of magmatic origin, forms inside of a silicate magma, and is emplaced via a hydrothermal fluid-mediated flotation mechanism. And these models are quite compelling because they account well for the magmatic and hydrothermal features that we see in IOA ore and in the geochemical features that we see in the ores themselves. However, despite this diverse array of models, there's still a lot of conjecture about how IOA deposits form and about which model would apply most broadly to IOA systems. So to take a closer look at the source and evolution of fluids in IOA deposits, I took a look at two distinctive IOA localities that are in the American Southwest, and I've shown just one here on this slide. This is the Buenavista system. It's located in north central Nevada, and it is characterized by really extensive sodium-rich alteration, over 900 cubic kilometers of scapolite and albite dominated alteration. The ores in this system take the form of replacive and massive ores, as well as brachyphils and the characteristic magnetite-apatite dikes that we see in a lot of IOA systems. And when I say that there's really extensive sodium-rich alteration, I really mean it. On the left-hand side, I've just shown a picture of some of the altered host rock from the system. The host rock is gabbro-diorite. And as you can see, this gabbro-diorite has been completely juiced. It's been almost completely replaced by scapolite and albite-rich alteration. And it was the recognition of this, as well as mass balance calculations between the igneous host rocks and the iron oxide ores themselves, that led Mark Barton's group to come up with the amagmatic hydrothermal model for these systems, which involves the circulation of basinally derived fluids and the formation of iron oxide ores via that circulation. So we took a closer look at the fluid evolution in this system by looking at the populations of fluid and melt inclusions that are hosted in apatite and actinolite and magnetite from this system. And I'm showing some pictures of that here. So for starters, there are abundant assemblages of brine inclusions that have compositions that can range from liquid vapor and halite, as shown in panel A, as well as assemblages that have more complex phases, phase assemblages. However, the microthermometric behavior for these inclusions is quite unusual, and I'm going to show a video of that here. And in particular, they show final melting above zero between a temperature range of +7 and +11 degrees C. So here I'm cooling this inclusion down and heating it back up from less than 100 degrees C. And you can see there's some melting behavior that's occurring as we approach zero. And now as we pass zero and approach 7, you see the abrupt decomposition of what we interpret to be a salt hydrate. I'll just show that one more time just in case anyone missed it. We're approaching zero and then right now. So this microthermometric behavior, like I said, is consistent with the decomposition of a salt hydrate, is inconsistent with the aqueous chloride solutions that we typically associate with a lot of mineralized systems. Instead, this behavior suggests a fluid composition that contains carbonate and sulfate as major constituents of the inclusion itself. So in order to test that interpretation, We took a look at crystalline residues that are present inside of breached inclusions, as well as the composition of decrepitate mounds that are precipitated onto silicate glass. And I have shown just some images of those here. On the left-hand side is a backscatter image of some opened inclusions showing their crystalline residue. And you can see that it has a composition that, among other things, is rich in carbon. And on the right-hand side is the decrepitate mound and the corresponding EDS spectra. And sure enough, it's got a composition that's rich in carbon and sulfur and sodium and chloride, among other things. And Raman analysis of these crystalline residues revealed the presence of high magnesium calcite within these residues. So all those things put together with the microthermometric behavior of these inclusions is consistent with a solution that's rich in both carbonate and sulfate. So this is probably the most important slide of the entire show. Associated with the brine inclusions are ubiquitous assemblages of polycrystalline inclusions. And I've just shown an image of that here in panel A. You can see the coexisting brine inclusions alongside the polycrystalline inclusions. And down here in C, I just show a photomicrograph of one of the polycrystalline inclusions. The analysis of polycrystalline inclusions that are exposed at the surface of the samples, like those that are shown here in the center in magnetite, as well as Raman analysis of polycrystalline inclusions that are hosted inside of apatite, indicate that these inclusions have compositions that are rich in carbonate, quartz, and iron oxide, mostly in the form of hematite. Furthermore, the microthermometric behavior of these inclusions is consistent with their formation at magmatic temperatures, and I'm just going to show that here in this video. I'll draw your attention to these features that are shown here in the center and in the top. These are little inclusions of aqueous liquid, and you're going to be able to see them deform as we reach high temperature, and a front of melting sweeps across the inclusion around 680 to 700 degrees C. So all of these observations together suggest that these polycrystalline inclusions represent entrapped carbonate-sulfate melt inclusions. What's more is that these inclusions, given that they have visible iron oxide phases and up to 5 to 10 weight% iron oxide, seem to be the most iron-rich fluids in this system, suggesting that the iron oxide mineralization was formed by these fluids. So this all begs the question, is this something that just occurs in Buenavista, or is this a feature that you can see in iron oxide systems elsewhere? To evaluate that question, we looked at another IOA system that's located in southwestern Utah, the Iron Springs system. The IOA mineralization in this system is associated with a monzonite intrusion. It occurs along the periphery of monzonite intrusions that are emplaced into evaporite and limestone-bearing sedimentary rocks. And you can see that actually pretty clearly in these pictures, where these topographic highs are the monzonite intrusions, and you can see the open pits for the iron oxide-apatite deposits are all around their periphery. And this system has both replacive and massive iron ores, as well as the characteristic magnetite-apatite dikes that have driven a lot of the conversation about IOA deposits. And these magnetite-apatite dikes have a lot of the characteristic features too, including things like columnar jointing, vesiculated center lines with euhedral crystals, and really well-developed syntaxial growth textures that are defined by apatite along their periphery. So what did we find when we looked at the apatite and magnetite-hosted inclusions in this system? Well, for one thing, we found nearly identical populations of brine-rich inclusions, and I've shown them here. And they're like identical to Buenavista, not just in terms of their phase assemblage, but also in terms of their microthermometric behavior, which similarly shows the very unusual melting behavior between 7 to 14 degrees C. I've just shown that here in this video. You can see the salt crystal has reacted with the ice during heating, and as we approach and pass zero, you're going to see it abruptly decompose and the salt crystal come back into view right now. I'll just roll that back one more time. And here we're at -8, and we're going to approach zero, and it's going to pop back into view around +8 degrees. There we go. So Just like in Buenavista, this unusual microthermometric behavior is consistent also with a solution that's rich in NaCl, carbonate, and sulfate-rich ions. So associated with all these brine inclusions throughout the paragenesis, and very unambiguously throughout the paragenesis of the iron spring system, are abundant assemblages of polycrystalline melt inclusions, or polycrystalline inclusions that are very similar to what we see in Buenavista. These are distinctive. They contain abundant carbonate, but are mostly dominated by sulfate, anhydrite, and gypsum. And similar to Buenavista, have abundant iron oxide phases, including goethite and hematite. And similar to Buenavista, they also show high temperature behavior that's consistent with formation at magmatic conditions. And in this particular inclusion that I've shown here, you're going to see several phases melting along its periphery. You see some phases that are melting in the left-hand side there, and then the bulk of the inclusion is going to disappear when we reach magmatic conditions. And you can actually see the hematite phase inside there shrink as well. So all these observations taken together, just like Buenavista, suggest that the polycrystalline inclusions in iron springs also represent carbonate and sulfate melt inclusions. And similar to Buenavista, these carbonate sulfate melt inclusions are the most iron-rich phase within this system, indicating that the iron oxide mineralization in this system is related to the circulation of and precipitation from these fluids. So all of this, offers the question of, where does this carbonate sulfate melt come from? Well, in all of these systems, there's no evidence of highly evolved alkaline magmatism, nor is there any evidence of a carbonatite complex or mantle-derived carbonatite complex at depth. Instead, we look to the cross-cutting relation, the common cross-cutting relationship of carbonate and evaporate sediments in these systems, which indicates that the carbonate and sulfate melts arise from the anatexis of these carbonate and evaporate bearing strata. Several experimental studies that have looked at the phase relations in carbonate bearing systems, like the one I've shown here on the left-hand side of this slide, indicate that the eutectic for many carbonate systems can be as low as 650 degrees C, and sometimes much lower in the presence of excess H2O and NaCl. And this would indicate that indeed that this temperature is well below the wet solidus of a lot of mafic and intermediate systems. And that, together with this experimental modeling, indicates that the melting of carbonate and evaporite bearing carbonate strata can certainly occur in these systems. So to test this, crustally derived carbonate sulfate melt interpretation, we looked at the carbon and oxygen isotopes from the IOA ore in the Buenavista system and compared it to the carbon and oxygen isotopes from fresh limestone distal from the gabbro-diorite contact, as well as limestone samples that are approaching and up against the contact with that gabbro-diorite. And we also did some Rayleigh fractionation modeling using the distal carbonates as a starting point. And the analysis showed two different fractionation trends for carbonate in this system, one that follows a low temperature path and another that follows a high temperature path. And I've also shown on this diagram a box showing mantle-derived carbonatite, carbon and oxygen isotope signatures. The signature of the IOA ore is not consistent with a mantle-derived origin and is instead consistent with distal limestone that has fractionated via high-temperature processes and has re-equilibrated with the gabbro. So this data together suggests that the carbonate inside of this system was locally derived and was sourced by the interaction between that carbonate and the gabbro-diorite intrusions in this system. So from that, we come up with the model that I've shown here on the right-hand side of this slide, in which you have a gabbro-diorite intrusion that's intruding into evaporite-bearing carbonate sediment, and you get melting anatexis that occurs along the periphery, or rather along that contact. The carbonate and sulfate-rich liquid will equilibrate with the melt as well as with the mafic country rocks and acquire the iron from that equilibration and leaching. And the upward circulation and eventual cooling and unmixing of this solution results in the precipitation of iron and apatite in this system, and the outward egress of spent ore fluid as well as the residual brine accounts for the formation of the sodic calcic alteration that's characteristic of these systems. And over time, the sustained generation of carbonate-sulfate melt leads to the formation of the large carbonate and apatite dikes that we observe in the Buenavista system and that are observed in IOA systems elsewhere. So one final note, does this model that I've described here apply to other iron oxide apatite systems? Well, we looked at the geology that's associated with a number of iron oxide apatite systems and noted that several notable examples feature geology that's very similar to what we see in the two systems in Iron Springs and in Buenavista. Mainly that you have mafic to intermediate intrusions that are cross-cutting evaporite-bearing sedimentary rocks. And in many of these systems, particularly the Iranian examples and the IOA deposits that are in the Ningwa and Luzon Basin have unambiguous evidence for the assimilation of carbonate bearing, or rather evaporite bearing carbonate rock. And in particular, also in El Laco, you have evidence in the nearby volcanoes of those volcanoes actually erupting pieces of skarnized evaporite and carbonate rock. So all these things together, given that it has the same geologic context, very similar ore textures, would suggest that this process that we've described here is common to IOA systems elsewhere. And with that, thank you so much for your time.
Thank you so much, Wyatt.
Thanks a lot, Marion and Irene, for the invite to comment on Wyatt's work, and thanks to Matt, who actually invited me to witness Wyatt's landmark defense. And obviously I'd seen your Nature Geoscience paper, Wyatt, which was outstanding, and to outline how outstanding it was, James Brennan added a comment to Nature Geoscience, and it's already getting citations, as this will. And kudos again to the supervisor, Matt McGinnis-Steele, for working on this cutting edge type of research. So eventually I need to ask a question, but I first wanted to mention a few things. Wyatt, first, I actually have to take off in a few minutes because I host an Atlantic Geology Society meeting in a few minutes. I have been to Iron Springs. I took a group of students on an SEG field trip in that region, and we specifically visited Iron Springs because I'm a friend of Dan Barker's, much older than me, but if you read through some of the literature, you'll see some of his stuff on peralkaline rocks, carbonatites, and so on was really key. And his paper on Iron Springs in 1995, Economic Geology, is an outstanding piece of work considering the limited knowledge that they had at that time. So anyway, fascinating area, and I'm glad that you were able to pick up and run with that to the next level. Your association with various evaporite carbonate horizons, I think, is absolutely fundamental. I think many people working in these environments, they're either compelled by the one idea that in essence is really spearheaded by Mark Barton's classic works. But as you know, some of these things never really fit well, especially the magnetite compositions that many people have contributed to. And you're right on, Adam Simon's work that he presented here is absolutely outstanding in recognition and trying to reconcile these issues. And so I think that this real observation, real analysis of these systems is important. I do want to acknowledge that I thought Jim Mungall's paper in Geology related to melting of phosphatic sediments is somewhat similar with different evidence to some of the assertions you're making. And then the other thing that I'd like to note is that the people at China University of Geosciences in Wuhan, China, that I specifically work with, have been working on some of these ideas for many years, and we published I think it's a classic paper that Adam Simon was reviewer of a brachiodiatreme associated with the Mesozoic skarns that are in the Dai district. And some of those papers, as well as Guang Wen's from the North Sediment Sequence sitting on the North China Craton, are very, very similar. And I got to work with these people on these very ideas. And so that leads to the point, my question, which is, in the study that Guang Wen had done, as well as even in the Dai district in China that I got to work on, was reconciling the hydrothermal reaction at very high temperatures that is possible, the melting and reaction of these versus the reaction and assimilation with exchange reactions at magmatic temperatures. Now, I mention that because you know this, because Matt and Bernard Chalier, actually, who's on the line, actually had presented this in a Quebec meeting a little over a year ago to kind of reconcile these high temperature exchange reactions with the magnetite, high titanium, vanadium magnetite assemblage that we saw. So I wanted you to comment on that if you've seen anything that would indicate some high temperature assimilation processes, which you actually did allude to, but you didn't talk about in detail. So that's my main question. Thanks.
Yeah, in these, I guess in these systems, you know, they don't, I didn't observe any of the actual, like, you know, evidence like we see in the Iranian deposits or in the Luzon and Ningguang Basin, where we have, you know, actual, visible evidence of the assimilation of the rock by the actual intrusion itself. You know, other than the fact that you have carbonate-sulfate melts that are circulating throughout this system. So, I mean, I guess we have, you know, evidence of the melting itself, but the assimilation is, you know, that's still kind of an open question. You know, the other thing I would say is the fact that we have these iron oxide rich ore bodies indicates that there's a certain amount of, or rather that there's abundant oxidation going on. And there's actually magnetite and carbonate that's in the intrusions themselves. And, you know, I did some mapping that was along that boundary in Buenavista between the intrusion and the limestone sediment itself. And I had noted that you have an increasing amount of magnetic susceptibility as you approach that contact with the limestone and the gabbro-diorite itself. And that, to me, suggests that you're getting some of that oxidation that's occurring within the melt itself because of that assimilation that's going on along its periphery. So, I mean, yeah, I guess I'm not totally certain how to answer that question, but I think that that would be the best evidence I have for that in these systems.
Yeah, well, in that abstract, but also there is other literature related to this. It's kind of interesting because some of these intrusions, like gabbro-diorite, and in the end, ferrodiorite, are some of the magmatic systems that have been postulated to have immiscibility naturally within them, as Bernard Chalier has really well demonstrated, as well as a few other authors. So in the end, is the assimilation reactions that produce CO2 actually a oxidant to those magmatic systems that has to happen at high temperature? And so in those cases, what would be that evidence that you might look for? And I would say that they would be high temperature hypersolidus endoskarns that are kind of hard to recognize unless you have a lot of good exposure and analyses. I've seen these, and a lot of people would say that, yeah, I've been smoking too much weed, but they are quite weird with large andradite endoskarns that are surrounded by feldspars and plagioclase, magmatic reaction system. So my point is that this is part of the story. It's an important end member part of the story, but there's a lot more to do, and hopefully you get to do that. Work on some of those questions too as part of your career. You haven't solved everything yet, Wyatt. That's what I'm saying.
That's a good segue for me.
Great. I have to leave. Sorry.
Thank you so much.
Thank you very much. Take care and congratulations again. And take it over there, John.
Okay, thanks, Dave. But Wyatt, did you want to comment on what Dave just said before I ask you? I've got a couple of quick questions then.
No, you can go ahead.
Okay, so great. So much like Dave, great talk. And I really enjoyed the live fluid inclusion show. I mean, anybody who's spent time doing fluid inclusions loves to see videos of fluid inclusion. So that was a really nice touch to your talk. So, and really interesting results. These are, as you point out, very controversial deposits, and for lots of good reasons. And so I guess my principal caveat to you would be, and recognizing that in order to make a splash in Nature Geoscience, you've got to be pretty strident in putting a position out there. But you're not done yet, would be my caveat. There's been many examples of people solving IOAs and IOCGs, and then we've gone back to the drawing board several times. So I'm not saying you're wrong. I'm just saying that watch this space. And on that, the Southwest US is an interesting place with these occurrences, but they're really occurrences on the world scale compared to the Karunas of the world or the IOA, the Iron Belt, which is 2,000 kilometers long through Chile and Peru, which are metallogenic scale processes. So whatever model we come up with, you have to explain things at the scale of the deposits and the fluids, which you're doing, have added a fantastic contribution to, but you've also got to somehow explain the scale at which this happens metallogenically. So why is it that we have this belt? Why do we have Carajás? Why do we have the Karuna district? The Karuna district isn't just Karuna, it's numerous other iron deposits and a significant amount of copper, although not of economic importance. So that's my kind of question to you, is think about the other scales. Obviously, I'd love to see you do this work, try to do this work elsewhere. Karuna be a prime example to do, but the deposits obviously in Chile, Peru would be other great examples. So any thoughts?
Yeah, in terms of thinking about this more broadly, I think about Dave Lentz's work looking at the generation or carbonate melting and skarn systems, and I think that there's from the experimental models that there's a number of different scenarios for how this can happen, and I don't at all think that it's isolated to just one process. We've had a number of IOA IOCG talks this year that have described magmatic and hydrothermal processes. And I think about something Tobias Schlegel said in his talk on IOCG systems, and that's that like everybody's right. And I think about something that Dave Lentz said in his talk that he gave earlier this year, when he did an overview of iron oxide mineralization in a number of different systems, that there's a number of routes that these systems can result in extreme iron enrichment. So, I think, we did this study and found a very compelling, similar observation in these systems. And I would assume that in systems that have the same cross-cutting relationships, you're going to make that observation. But I by no means mean to say that this is the only way that you can, form these very, iron oxide and magnetite-rich systems like this. But, I think the main question, or like one of the main problems that we have when we think about these systems is how do you mobilize and precipitate iron oxide, and specifically what type of fluid? I guess the basic question is, what type of fluid do you need to do that? And the special thing about the carbonate-sulfate melts is such that you can partition a lot of iron as well as other things like titanium and rare earth elements into that solution. But there's research that also shows that under the right conditions, especially under reducing conditions, you can partition a lot of iron into chloride solutions, and that magmas, particularly those things like phosphorites that have a very clear orthomagmatic association, like those systems can reach really high iron enrichment and have a very similar composition. So I think that this is likely a snapshot of a process that operates in many iron oxide systems, but is by no means the only process that's operating in iron oxide and IOCG formation.
No, I appreciate that. That's great response. Yeah, it'd be, I say, interesting to go to some other places. No, you're not so far from you. On the other side of the mountains at Afton in Kamloops, just outside Kamloops, there's magnetite-apatite veins there associated with the alkaline plutonic complexes. And this is an arc complex with alkaline, subalkaline volcanism. No, as far as I'm aware, evaporites or any evidence for evaporites because you're in a marine arc site setting. So it'd be really interesting to look at those samples. And my question then would be, is there any other way you could generate carbonate sulfate melts other than involving external sources of carbonate and sulfate? And because I think the idea of carbonate sulfate melts is very intriguing.
Mm-hmm. I mean, in the New Afton, I'm not totally familiar with that system. I know it's a porphyry deposit, and they're associated with magmas. And as we see from looking at magma evolution, particularly in carbonatite systems, we know that in the end stages, like at really high degrees of fractionation, that you get more of these more unusual compositions, things that are rich in carbonate and rich in sulfate, and that's obviously one of the models that we have.
That's probably not the case there, but it's I know that's fair enough. Yeah, these are source of diorite monzonites, the intrusions. So they get a little bit maybe more fractured in that, but they're not extreme fractionation there. But the beautiful magnetite-apatite veins. This, again, it's small. I'd actually much rather you worked on something really big and significant like Karuna. Anyway, we should probably let somebody else get in there with a question. But really enjoyed your talk. Excellent piece of work, and I loved your fluid inclusion. I had some other detailed questions on that, but I'll send you an email or something to get those.
Thank you so much.
Thank you, Wyatt. I have one question regarding if there's any, do you think if there's any specific tectonic set-in that is able to, that it can be related to IOA systems, or do you think it's mainly the fact that you have to have evaporitic rocks in the country rock?
I mean, that's a really good question, and I think that kind of relates to the last conversation we were just having about these larger scale processes. And I think the two main ingredients here is that we have these extensive packages of evaporites and carbonates, and then we have magma generation. So I think anywhere where you get this more mafic and intermediate magma generation, whether it's in the Andean Arc or in the Great Basin, that as long as you have that cross-cutting relationship, the process that we've described here can occur. And I think the diversity of these systems across the world kind of speaks to the fact that there's a lot of different ways that you can have this chemical process occur and have the melting process that we've described here occur. So I mean, I guess I'm not saying that there's not a specific tectonic setting that's associated with this. I don't necessarily know the answer to that question, but like I said before, I feel like there's a lot of different ways that you can arrive at this, the scenario that we've described here, as well as a way that you can arrive at iron enrichment in a number of different environments.
Thank you. So we have one question from our attendants, from Leslie Logan. Leslie, I'm gonna unmute you so you can ask your question.
Okay. Hi, thanks for your talk. Had a bit more of a simple question, I think. I didn't really catch from your description from the deposits, actually, if they were hematite dominated or magnetite. But then
they're made. Go on.
Magnetite.
Yeah, they're mostly the main ore bodies themselves are magnetite dominated, and I know Buenavista has some hematite ore bodies that are around its periphery, and in Iron Springs, same thing. It's dominantly, I mean, they're massive magnetite rocks for the most part, with minor hematite as well.
Okay, so yeah, I was kind of curious about the hematite crystals. You were saying those were the more common iron oxides you found in your fluid inclusions. So I thought I would ask a little bit if that's hematite, or if that's hematite after magnetite, or if there's something more compositionally that you found out about them. I don't know if you used Raman or if you did like in situ laser ablation on your inclusions, but I don't know how much compositional information you have. So I was just a little bit curious about the hematite versus it being magnetite in your inclusion.
Oh, sure, that's a great question. Though for one thing, the idea of hematite inside the inclusions, that's constrained from both EDS analysis of the open inclusions and Raman. But You know, that very same question has come up in some of the reviews of this work, and that is very curious. Like, why don't we see an assemblage that has magnetite rather than hematite? Specifically, you know, particularly because, you know, these are magnetite-dominated ore bodies. But these inclusions, you know, I think inclusions generally commonly show diffusion of water, diffusion of hydrogen out, and that diffusion of hydrogen can drive the formation of hematite. Can drive the conversion of magnetite to hematite within these inclusions. So I feel like that accounts for the hematite rather than, you know, the hematite dominated composition rather than a magnetite dominated composition. And I think that's backed up by the fact that at really high temperature, we see in some cases, we see incomplete melting of the opaque crystal. We can see it shrink, and it'll shrink in size by about, you know, like 50–60%, but it won't completely homogenize at high temperature. And that's another kind of hallmark of hydrogen diffusion out of these inclusions.
Okay. Is there something more that you could get, like composition wise, that would like help trace it to being magnetite, like a high titanium signature or something that stays? I don't know if you could really detect that.
Yeah, I guess I'm not quite sure how to answer that question. You know, another part of the phase assemblage here that we commonly observed was anatase in the inclusions themselves. So, you know, there's clearly a lot of titanium that's in these inclusions, you know, pretty routinely, both particularly in Buenavista, but to a lesser extent in Iron Springs. So, you know, perhaps that points to, you know, magnetite, or rather hematite after magnetite in these inclusions, but I'm not quite sure. That's a really good question.
Yeah. Okay, that's super interesting. So thanks.
Thank you.
Hey, I don't know. We don't have any more questions in our chat, unless there's any questions in YouTube.
No, I don't see any question on YouTube. So we should shortly move on to the next talk. But maybe before finishing, Wyatt, I know everyone said you're not done with this topic, but what are you working on at the moment, and what is your plans for the future? Are you still working on this deposit?
Yeah, I'm doing some follow-up work. I wanted to do some laser ablation on the inclusions themselves, as well as look at some other IOA deposits. I've also, I have a project, or I'm cultivating a project that's looking at the origin of ferrocarbonatite systems and their enrichment in iron, as well as the role of aqueous carbonic fluids in forming those systems. So, you know, some work that's still kind of in the iron oxide realm, but maybe a different flavor of iron oxide deposits. And I also kind of wanted to kind of focus on IOCG systems. I have kind of a project in the initial stages looking at an IOCG system that's located in California, and looking at essentially, you know, rather evaluating the degree to which carbonated assimilation might have played a role in that. And, you know, kind of relating back to what Dave Lentz had asked about, and looking for the signature of assimilation, and, you know, essentially trying to see how much carbonated assimilation or rather what role carbonated assimilation might play in the rare earth element enrichment in IOCG systems. So, like I said, a lot more work on iron oxide systems, and you know, specifically looking at some of these more rare earth element enriched varieties.
Sorry, I got to just jump in very quickly with a quick question or follow up on that. So have you looked at that, or are you able to look at some of the intrusions to see if you can see any of the signatures actually in the magmatic rocks, or are they too altered to, you know, too sodium altered to be helpful?
No, and that's exactly some of the follow-up work that we want to do, and in particular, you know, there was some experimental work by Rajiv Das Gupta at Rice University that had looked at how carbonated assimilation would affect the trace and major element compositions of the primary silicate phases in those magmas. And specifically, as you might guess, you know, the silicate phases become more enriched in calcium and magnesium as you approach or rather, we would expect to see the silicate phases become more enriched in calcium and magnesium as we approach the contact with the limestone. And correspondingly, we would expect to see, you know, if the iron oxide if the iron oxide ore deposits are being formed by essentially this like equilibration between, melts that are forming along the periphery and the, silicate system, we would expect to see some of that depletion in iron as well as rare earth elements in the intrusion, and see that same sort of spatial trend. And, I did, like I said, I had done some mapping in Buenavista, and I think the preliminary work shows that you do see that, you do see that basic spatial trend, and especially you see, more of that iron oxide enrichment that sort of grades from the intrusion into the deposits themselves. So, yeah, and I also, I think that the same sorts of trends would probably be seen in terms of the sulfur isotopes in the intrusion itself, as well as the carbon and oxygen isotopes of carbonate, if you have that in the intrusion, where you'd have, a kind of a increasing trend towards its contact with the limestone in terms of its, the carbon and oxygen isotope signature of that carbonate being more like the limestone itself.
Well, thank you so much, Wyatt, for such an interesting talk and for answering these very interesting questions also. I will be waiting for your future work and being able to read it.